You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. When organizations design modern computing systems, they face an array of choices in how workloads are packaged, deployed, and managed. This decision is not merely technical. It touches risk, performance, cost, and the human effort required to keep systems running. The broad term compute abstraction captures the different layers at which computing environments can be represented, from fully virtualized operating systems to lightweight containers to ephemeral serverless functions. Each abstraction provides a different blend of isolation, efficiency, and responsibility, and each aligns more naturally with certain use cases than others. By exploring these models, we gain the ability to match a workload to the best execution environment. Doing so ensures that risk is balanced with efficiency, that performance expectations are met, and that operational overhead is aligned with organizational goals rather than working against them. Compute abstraction is essentially the act of wrapping computing resources in a standard layer that makes them easier to manage and deploy. Think of it like choosing packaging for a product. A fragile item may be placed in a sturdy box with foam insulation, while a lightweight gadget could be shipped in a small padded envelope. Both items reach the customer, but the packaging determines efficiency, cost, and protection. In the same way, abstracting compute environments allows developers and operators to standardize how workloads are delivered, whether that means full machines, lighter containers, or serverless functions. This standardization reduces complexity and increases predictability, ensuring that no matter where the workload runs, it behaves in a familiar and controlled way. Without abstraction, every deployment would be bespoke, and security, performance, and management would suffer. Virtual machines, often referred to as VMs, are one of the oldest and most established forms of compute abstraction. A VM packages not just the application, but an entire operating system, including the kernel that governs core functions. This makes VMs highly versatile. They can run almost any software designed for that operating system. The trade-off is weight. Since each VM replicates a whole OS, they require more storage, more memory, and more processing power compared to other abstractions. However, this comes with benefits. Isolation between VMs is strong, which means that if one VM is compromised, the attacker has a much harder time reaching another. For workloads with high risk or compliance needs, this isolation makes VMs attractive. They function like renting an entire apartment rather than just a room, more space and responsibility, but also greater separation from your neighbors. Containers, by contrast, are designed to be lean. Instead of replicating the whole operating system, they share the host's kernel and package only the application and its dependencies. Imagine a shipping yard where goods are placed in standardized containers that all fit the same ships, trucks, and cranes. The contents differ, but the outside format is predictable. This efficiency makes containers quick to start, easy to scale, and highly portable. Developers can build an application on their laptop, package it into a container, and know that it will run the same way on a test server, in the cloud, or anywhere else that supports containers. The trade-off is that because containers share the host kernel, the boundaries between them are thinner than between VMs. Security controls must therefore be reinforced with additional layers, such as namespaces and access restrictions. Serverless computing takes abstraction even further, also called Function as a Service, or FaaS. This model removes the concept of servers entirely from the developer's perspective. Instead of provisioning machines or orchestrating containers, the developer simply writes a piece of code and defines the events that trigger it. The cloud provider handles the rest, provisioning resources, running the function, and tearing it down when finished. This is like summoning a taxi, only when needed, instead of owning a car. It offers tremendous efficiency for event-driven tasks, since you pay only for the actual execution time rather than idle capacity. The downside is reduced visibility and control. You cannot log into the underlying system or dictate how it is patched. This trade-off makes serverless best suited for workloads where simplicity and elasticity outweigh the need for detailed customization. The level of abstraction chosen defines where the lines of responsibility fall between the provider and the customer. With VMs, the customer retains control over the operating system, patching it, configuring it, and monitoring it. With containers, much of this responsibility shifts into shared models, where the orchestration platform may automate updates or enforce policies. With serverless, most of the infrastructure is opaque to the customer, who instead focuses on the application logic. Think of it like different dining experiences. Cooking at home means you handle everything yourself. Ordering takeout means someone else prepares it, but you still manage the setup. And dining at a restaurant means everything is handled for you, but you have no say in the kitchen process. Each level has benefits and constraints, and choosing wisely helps align expectations with reality. A central concept across VMs and containers is the idea of an image artifact. This is a fixed snapshot of the environment, essentially a recipe for building consistent execution environments again and again. With VMs, these images may be disk templates with a full OS and pre-installed software. With containers, they are lightweight images defined by configuration files such as Docker files. The importance of images lies in reproducibility. By locking down an environment in an image, organizations can ensure that every deployment, from development to production, behaves consistently. Images also aid in version control and provenance, providing a verifiable chain of how software was built, tested, and released. Without them, subtle differences between environments could cause unexpected failures or vulnerabilities. Orchestration platforms add another layer of sophistication, particularly in the world of containers. Kubernetes is the most well-known, serving as a system that automates container placement, scaling, networking, and recovery. Orchestration can be compared to an air traffic control tower, directing the constant flow of workloads across nodes in a cluster. It ensures that applications are balanced, that they restart if they fail, and that they can discover and communicate with one another. Without orchestration, managing dozens or hundreds of containers would become unmanageable. Instead, orchestration platforms enforce consistency and resilience at scale, making container adoption feasible for organizations of all sizes. This automation, however, comes with its own risks. Misconfigured orchestration can inadvertently expose services or introduce single points of failure. Autoscaling is one of the key benefits of abstracted compute environments, especially in cloud platforms. The idea is simple: increase resources when demand spikes and reduce them when it subsides. But the impact is profound. Without autoscaling, systems either remain underpowered during peaks or waste money sitting idle during lulls. Policies for autoscaling define how quickly and under what conditions this expansion or contraction occurs. For example, a web store may scale up when traffic surges on Black Friday, then scale back down overnight. The trick is balancing performance and cost. Too slow a response can lead to outages, while too aggressive scaling may trigger unnecessary expense. Proper tuning is essential, making autoscaling both a cost saver and a potential pitfall if poorly managed. Serverless computing, despite its advantages, introduces a unique challenge called cold start latency. This refers to the delay that occurs when a function is triggered but must first initialize its runtime environment before executing. For low traffic or sporadic workloads, this overhead might be negligible. But for latency-sensitive applications, such as financial transactions or real-time communication, even a short delay can cause disruption or diminish user experience. Developers sometimes mitigate this by keeping functions warm through periodic invocations, or by carefully tuning their code to reduce initialization requirements. The issue highlights an important truth about serverless. While it excels in elasticity and cost efficiency, it does not eliminate all performance concerns. In fact, its very design, ephemeral, on-demand execution, creates scenarios where responsiveness may lag just when demand spikes, making it vital to weigh suitability, before committing to this model. Another factor in choosing an abstraction is how it handles state. State refers to the persistence of data across sessions and executions. VMs, by virtue of running full operating systems, handle state natively with attached storage and memory. Containers also allow state, but the ephemeral nature of container instances often encourages developers to externalize data into databases or storage services. Serverless functions take this further by assuming complete statelessness, with each invocation being independent. Persisting information requires integrating with external storage like object stores or managed databases. The choice of abstraction must therefore align with the application's data model. If the workload demands continuous, in-memory state, such as a multiplayer game server, VMs or containers are better fits. For event-driven, stateless operations, like resizing images on upload, serverless shines, provided state is carefully managed outside the function boundary. Networking also differs significantly across compute abstractions, shaping security and architecture. In VMs, networking resembles traditional on-premises infrastructure, with virtual NICs, subnets, and firewalls that allow fine-grained control. Containers, however, require more nuanced handling. Because multiple containers share the same host, they often communicate over virtual bridges or overlays, making policies like ingress and egress control vital. Serverless abstracts networking further. Functions typically expose APIs or event triggers, but direct control over the underlying network is limited. This reduces complexity for developers, but places more reliance on the provider's controls, such as API gateways and IAM-based permissions. The implications are clear. While serverless reduces surface area by design, it also limits customization. Conversely, VMs offer the broadest flexibility but require the most operational effort. Understanding these differences is essential for designing secure and efficient systems that don't inadvertently leave doors open to attackers. Secrets management is another universal requirement across VMs, containers, and serverless. Applications rarely operate in isolation. They connect to databases, APIs, and services, all of which require credentials, keys, or tokens. Hard-coding these secrets into images or code is a dangerous practice, as it risks accidental exposure or theft. In VMs, secrets may be stored in configuration files or injected at runtime through secure vaults. Containers typically integrate with orchestration platforms that can mount secrets into memory without persisting them on disk. Serverless functions rely on environment variables or provider-managed secret stores. In every case, the principle remains. Secrets should be centrally managed, rotated regularly, and accessed only by authorized workloads. The abstraction chosen changes the mechanisms, but the responsibility remains constant. Failing in this area can quickly unravel even the strongest compute design, as attackers often look for weakly protected secrets as an entry point. Observability, the ability to monitor and understand what is happening inside a system, varies depending on the abstraction. VMs provide extensive visibility since operators can access system logs, install monitoring agents, and probe performance at the OS level. Containers offer less visibility into the host, but provide strong application-level metrics and logs, especially when integrated with orchestration frameworks that collect and centralize data. Serverless presents the greatest challenge. Since the infrastructure is abstracted away, visibility is limited to the metrics and logs provided by the cloud provider. Traces may show function invocations, execution time, and error rates, but not the underlying system details. This limitation forces teams to adapt their observability practices, often relying on external tracing and logging frameworks. The broader lesson is that as abstraction increases, direct insight decreases, requiring organizations to trust the provider's instrumentation and design their monitoring strategies around the available signals. Regulatory and compliance considerations also shift with abstraction. VMs give organizations maximum control and visibility, allowing them to meet detailed audit requirements by configuring systems to exact specifications. Containers provide similar control but require careful orchestration to maintain consistency across environments. Serverless, however, reduces visibility and moves responsibility for many controls to the provider. While this can simplify compliance in some cases, it can complicate others, where regulators demand direct access or custom configurations. For example, certain healthcare or financial standards may require proof of how systems are patched or secured, something more easily demonstrated in VMs than in serverless. The choice of abstraction thus has implications not just for technology, but for meeting external obligations. Organizations must carefully assess whether their compliance requirements align with the level of control and transparency available in each model. Cost is one of the most practical dimensions of abstraction differences. VMs typically operate on a per-instance billing model, where costs accrue as long as the machine is running, regardless of usage. Containers, especially in orchestrated environments, often follow similar patterns but can increase density by packing more workloads onto fewer hosts. Serverless introduces a per-invocation model, charging only for the precise execution time and resources consumed by each function. This makes serverless attractive for spiky or unpredictable workloads, where idle time would otherwise drive up costs. However, for steady, long-running tasks, serverless can quickly become more expensive than reserved VM or container capacity. The trade-off illustrates the importance of aligning billing models with workload behavior. Organizations that fail to map workload patterns to cost structures risk overspending, even if their technical design is sound. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.